Today we begin Chapter 5, and we'll start looking at graphing quadratic functions in standard form. First, let's knock out some vocabulary. Quadratic function is a function that can be written in a standard form of y equals ax squared plus bx plus c, with the condition that a is not equal to 0. If a was 0, the x squared term would drop out and you'd have a linear function. The graph of a quadratic function is a U-shaped graph that we call a parabola. The parent function, y equals x squared, is displayed here in your notes. A couple of important things to keep in mind about graphs of quadratic functions. The first is that it has a turning point. Unlike the linear functions that we've been dealing with, this one has a point where it changes direction. Later on in the year, we'll find some other types of functions that actually have more than one turning point. But for right now, we've got one turning point. We call it the vertex. That's also the highest or lowest point on the parabola. One of the other things about parabolas, as far as their characteristics that will make graphing them quite a bit easier, is that they are symmetric. Parabola has an axis of symmetry that divides the parabola into mirror images. So any point that exists on this side of the axis of symmetry has a mirror image on the opposite side as well. So to take a look at a couple of the characteristics about quadratics in standard form, what I asked my students to do in class today was to go ahead and take out their phone, open up the Desmos app, and to go ahead and take a look at a quadratic function, and to use the slider feature within Desmos to be able to go ahead and kind of discover what happens when we change the value of a, when we change the value of b, when we change the value of c. So entering in y equals ax squared plus bx plus c, and we're going to go ahead and add sliders to all three of those. Now, let's take a look at what happens when we manipulate the value of a. And we can slide that from values of -10 to +10 as a default. My students did this in class as well. And they saw that as they moved a, and the value of a got larger, absolute value of a got larger, the graph got more narrow. Once the absolute value of a dropped below 1, the graph started to get wider and wider and wider. There's a equals 0. We said that condition no longer is a quadratic. Now it's a linear function. And in Desmos, we can see that, a straight line. What happens when a becomes negative? Well, now, instead of a graph that opens up, we have a graph that opens down. And again, as the absolute value of a gets larger, the graph gets more narrow. So two things happen. Changing the a value changes the width of the graph, and changes whether it opens up or down. How about when we manipulate the b value? This one was a little bit tougher to see because it's moving not only side to side, but also as the b value moves, we're going to find out in a minute, that the c also has something to do with it here. But the b value allows the graph to move side to side, so changing the b value moves the graph side to side. And how about when we change the c value? Now our graph is moving up and down. So we took some time in class to discover what happens to the graph visually when we change the value of a, b, or c. Now we want to think about graphing a parabola. We've got a set of steps that we're going to follow to be able to graph a parabola. And what we're going to find out is you could sit down and put your shoulder to the wheel and grind out 5 ordered pairs, plot those on the graph, and run a parabola through them. But it turns out that if we play our cards right, we actually don't have to substitute in 5 x values. We could get away with 3, and if we catch a break, just 2. If you were here in class with us the other day, we did a little axis of symmetry discovery exercise. Some of the students, one student in the pair had the x values 1, 2, 3, 4, and 5 for a function. The other student in the pair had -2, -1, 0, 1, and 2 for the same function. And those are very common sets of numbers for a table of values. 1, 2, 3, 4, 5 when students first started graphing in middle school, -2, -1, 0, 1, and 2 from Algebra 1 on. And what we found out in the discovery exercise is neither one of those gave us a really full picture of what this parabola graph looked like. So it turns out that we need to come up with our own custom set of x inputs for our table of values. And so we're going to follow these steps to make that happen. So to graph y equals ax squared plus bx plus c, a standard form of a quadratic function, first we need to find the axis of symmetry, which is given by the formula x equals opposite of b divided by 2a. Then we're going to locate the vertex. Now, the vertex always lives on the axis of symmetry. So this x value, which is the equation of a vertical line, that x value is going to be the x coordinate of our vertex. We'll plug it into the function and find the y. We'll plot that. Then we'll pick 2 points that are on one side or the other of that line of symmetry, locate those points, and we know we have mirror images on the opposite side, and then we can go ahead and draw our parabola. So let's take a look at an example. We're going to graph the function y equals x squared plus 6x minus 2. And I'm going to go ahead and change the scale on my graph. Make each of these boxes equal to 2. -4, -6, -8, -10. So our first step, find the axis of symmetry. So x equals the opposite of b over 2a. Now, where does this a, b, and c come from? I see y's and x's. Remember, y equals ax squared plus bx plus c, our standard form. A is the multiplier on x squared. B is my multiplier on x. C is my constant. So let's go to the equation. My c value is the constant, -2. Got to keep the sign with it. My b value is the multiplier on x, which is 6. Understood that that's 1x squared, so my a value is 1. Now let's substitute those in. The opposite of 6 over 2 times 1. So I have -6 over 2. So the equation of my axis of symmetry is x equals -3. And I'm going to go to my coordinate plane, and I'm going to draw in that axis of symmetry right now. I want to get a visual on this as I go to work through the graph. Second, I need to find the coordinates of the vertex. Now we know the vertex lives on the axis of symmetry, so I just need to substitute that value in. I need f of -3. So -3 squared plus 6x minus 2. 9 minus 18 minus 2. That's -9 minus 2. That's -11. So my vertex is at -3, -11. I'm going to mark that on my graph right now. -2, -4, -6, -8, -10, -11 is right about there. Now, step 3, table of values. We said we were going to generate a custom set. My axis of symmetry, I'm going to make the middle point of my 5 x values. I'm going to put a box around it because that's my vertex. I just found out that when I substitute in -3 for x, my y is -11. I've plotted that point already. Now I need 2 more points here and 2 more points here. This is why the axis of symmetry dotted line on my graph is such a great visual. You can think about looking at the x-axis as a number line. I'm at -3. I need 2 x values that are to the right of it. Well, now I can see -2 and negative 1 are going to work perfectly. 2 points to the left, negative 4 and negative 5. None of us would ever off the top of our head say, hey, let's put in negative 1, negative 2, negative 3, negative 4, and negative 5 for x values. We only would have come up with those by locating the axis of symmetry first, making that the middle number of our 5, and then going back in. Why do we want to do that? Well, because of symmetry, whatever my y value is for negative 2, so is my y value for negative 4. Whatever negative 1 turns out to be, so is negative 5. I only need to plug in 2 more values, and I'll be able to fill out my table of values. Now, if one of these were 0, I'd hit the jackpot, because look what happens when I substitute in 0. X squared, 0 times 0, that's going to be 0. 6 times x, 6 times 0 would be 0. If x is 0, the first 2 terms drop out. All I have left is my constant. It's my y-intercept. So if one of my x values that I need to locate is 0, I can not only plug in that constant here, but here as well. We didn't catch that kind of a break, though, on this one. So let's go ahead and plow through these. I need f of negative 2. So negative 2 squared plus 6 times negative 2 minus 2. 4 minus 12 minus 2. 4 minus 12 is negative 8 minus 2 is negative 10. So when I substitute in negative 2, my y value is negative 10. By symmetry, 1 unit right of the axis of symmetry was negative 10. I go 1 unit left of the axis of symmetry, negative 10. So let's go ahead and plot those 2 points right away. Okay, 1 left. I could either put in negative 1, negative 5. Most of us, I think, like to operate with the smaller absolute value numbers if we can, the ones closest to 0. So let's do f of negative 1. Negative 1 squared plus 6 times negative 1 minus 2. 1 minus 6 minus 2. So that's negative 5 minus 2, that's negative 7. When I put in negative 1, my y value is negative 7. And by symmetry, I know the same is true when I substitute in negative 5. Last thing I need to do is draw my parabola. Important point here is this is not a dot to dot. I'm not drawing line segments to connect these points. It's a smooth curve. Something like that. There was one more practice problem on the in-class set. I'm going to jump over that. I'm going to take a look at number 3. We're going to take this expression and we're going to rewrite this in standard form. Y equals negative 3 times the quantity x minus 4 times the quantity x plus 2. Well, if you remember multiplying binomials together, it's the distributive property twice. X times x is x squared. X times 2 is 2x. Then I have negative 4 times x, so minus 4x. Negative 4 times 2 is negative 8. Let's combine like terms. X squared minus 2x minus 8. Now I can distribute the 3. Negative 3 times x squared, negative 3x squared. Negative 3 times negative 2x, that's positive 6x. Negative 3 times negative 8, plus 24. And now I have an equation that's quadratic, and it's written in standard form. Y equals negative 3x squared plus 6x plus 24.